The, the first speaker today is Hosseini, who is going to tell us about symmetry descent, symmetry TFT from dimensional reduction. Please start.
Yeah, it's on.
Okay, it's better? Okay. Thank you for the introduction, and thank you very much for inviting me. It's great to be here, and thank you for organizing this very interesting conference. So today I'd like to tell you about symmetry descent, and this idea came about when we were trying to study symmetry TFTs from dimensional reduction. This is based on some earlier works from a few years ago with Fabio Abruzzi, Federico Bonetti, Iñaki Garcia-Echeverri, and Sakura Shefranomeki, and some more recent works we did together with Iñaki earlier this year, as well as some work that's to appear with Yuji Tachikawa and Hao, who is here. Okay, so starting from the theme of the conference, topological operators, these are define our symmetries. And these topological subsector of the theory that describes the symmetries can often be understood in terms of a topological field theory in one dimension higher. And this topological field theory goes by the name of symmetry topological field theory, or symmetry theory, or SymTFT for short. And it tells us about all the possible symmetries and their anomalies and all the possible topological structures in the sense of symmetries that the theory can realize in one lower dimension. And there has been so many works by people here in the audience as well on trying to understand these symmetries from this perspective. Also, there are also sometimes TFTs. There are these one-dimensional higher theories which describe the symmetries, and they are not topologicals, but I'm not going to discuss those. Okay, so before getting into the details, let me just try to give you an overview of what I'm talking about. So very quickly, I'd like to go over some other ideas about anomalies, anomaly theory, and anomaly descent. And then I'd like to generalize to symmetry TFTs and tell you how it knows about the different traces of symmetries and their anomalies. Then I will go on to tell you about symmetry descent. Again, so this symmetry descent comes about when we try to think about symmetry TFTs from dimensional reduction, but well, you can define them on their own. They doesn't have to be in terms of dimensional reduction. And to clarify what I mean, I will give you the example of 4D Maxwell theory, which you're familiar with, and I tell you how to reduce it on a tree manifold to get a one-dimensional topological field theory. And the way I like to do this is by constructing an action in one higher dimension for Maxwell theory that realizes Maxwell theory as an edge mode. Yes.
Okay.
Okay. Thanks. And when we're doing the dimensional reduction, so as I said, I want to construct a bulk action for Maxwell in one dimension higher and then reduce that on a tree manifold. That gives me a two-dimensional theory. And then using a Stokes term, I can get the one-dimensional TFT. And one thing is important is that when we do this dimensional reduction, we are, to get this non-trivial CFT, we are interested to reduce our theory on manifolds which are topologically non-trivial. And so we have to think about how to encode that in the gauge fields to be topologically non-trivial. So we'll discuss that too. And then you might ask, why do I want to go to 5 dimension to do this dimensional reduction to study these TFTs? And this is particularly important when we consider theories which have fields which are self-dual. Well, here in Maxwell theory, we have electromagnetic duality, and here we also like to treat both electric field and the magnetic field on equal footing, and going to a bulk constructions let us do that very easily. And in particular, the examples I'm interested in are string theory examples, and here the fields are given by self-dual fields. So to see the full symmetry TFT, for example, the BF sector, which tells us about the choices of symmetries, we can only see those symmetries in a Lagrangian formulation if we construct bulk actions for a string theory. And this is very interesting to look at these constructions, because there are just so many interesting theories one can study from a string theory, and this method gives us a systematic way in principle to study all the possible symmetries of a given QFT that we can construct in that way. One thing to mention is that to construct actions for a bulk action for a string theory, we need to make sure that it is consistent with anomaly cancellation conditions. And for example, in type 1 string theory, we want to make sure we satisfy the Green-Schwarz anomaly cancellation. And so I will discuss that briefly. Also, we can understand this Green-Schwarz anomaly cancellation from a more modern perspective in terms of anomalies of higher form symmetries, and that's interesting on its own. So I'd like to mention that. Okay. So let me try to be more specific by what I mean by symmetry TFT. So let's start with assuming that we have no anomalies, and focus on a simple example for this super-Yang theory that you're familiar with. Here, I'm taking the Lie algebra to be SU2 for simplicity. And we know that this theory has different choices of symmetries. So if you just take the Lie algebra to be SU2, you can have different line operators in your theory. They can be two lines or Wilson lines or Dionic lines, and you cannot have all of them at the same time in the theory because of direct quantization convention. They cannot be local simultaneously in the theory. So depending on which of these you have different associated symmetries to these. So there are choices of Z2 one-form electric symmetry, Z2 one-form magnetic symmetry, and Z2 one-form Dionic symmetries. And these different choices, they can be encoded again in a topological filter in one dimension higher, which is called the BF theory. It has action B with F, and F is dA here. So this theory has some gapped boundary on the left, and different choices of boundary conditions for these fields B and A. They tell you the different possible choices of symmetries that this theory that lives on the boundary can realize. So these we can have three-shaded boundary condition for B or for A, and they could be operators that we can construct in the bulk that end on the boundary or don't, and then the ones that end on the boundary give us the topology. They give us the objects which are charged under the symmetry, or they could give us the objects which are the topological operators if they don't end on the boundary. Now this can be generalized to any dimension. So if T is a d-dimensional theory, we call the relative theory because this symmetry is not fixed and is defined relative to this higher dimensional theory. And again, this BF theory with higher form fields B and A can describe the different choices of symmetries on the boundary. So here in d dimensions, I have P form symmetry, or I can have the dual D minus P minus 4 form symmetry, and choosing boundary condition for these fields B and A, I get the different choices of symmetries on the boundary. So in general, we have this non-invertible topological field theory, which describes the choices of symmetries. And once we fix the boundary conditions, we pick one of the boundary conditions for this theory. We just kind of collapse this yellow part, and so we basically write an action for this gapped boundary and add it here. We integrate over the fields which are dynamical here, and then we get a theory on the boundary which has a fixed symmetry. Now, let's forget for a second about choices of symmetry and say we have a theory T which has anomaly G. And then how do we describe the anomaly of this theory? So we know that we can use anomaly theory to describe it. So the anomaly theory is an invertible topological field theory, often given by a Chern-Simon theory, and it describes the anomalies of this theory T with symmetry G. But what if we have not fixed the theory to have this symmetry G, and then how do we describe the possible anomalies of this theory? That would be a relative theory like we had in the last slide. So this is where the SymTFT description is very useful. Here we can define a theory in D+1 dimensions, which knows about not just the choices of symmetries, but also the anomalies of these different possible symmetries. And then when we fix this gapped boundary, we specify boundary conditions for this theory, and we get a theory with a fixed symmetry and together with its anomaly theory. Okay, so now how do we obtain this symmetry TFT from dimensional reduction, which is in the title of the talk? So what we want to do is start from some theory on y times L. So this could be the Maxwell theory on y times L. And we are taking L to be a closed manifold, so it doesn't have a boundary. And when we reduce on L, we want to get the symmetry TFT on Y. So here, starting from 4D Maxwell, we go to one-dimensional TFT. And like I said, we want to construct a bulk action for Maxwell. So we extend this theory to one dimension higher. So basically, we define a theory on Z times L, which realizes Maxwell as an edge mode. And then we can integrate over L. We will see that the gauge degrees of freedom in this theory will give us the boundary mode. So the gauge degrees of freedom in Z will, so if we, so when we do the dimensional reduction of this action we defined in D+1 dimensions, then we do a gauge transformation. So here I have doing the reduction, I get S of inflow, the action for on Z, and then looking at the gauge transformation, I get the D of the SymTFT action. So I'll make that more clear in the examples. So let me, okay, so let me just be more clear what I mean by symmetry inflow and this symmetry descent. So let's review the anomaly of inflow that most people are familiar with here. We have a topological filter, which is the anomaly theory in D+1 dimension, describing the anomaly G of a D-dimensional theory. And B here is the background for the symmetry G of the D-dimensional theory. We also have an anomaly polynomial in D+2 dimension, which is given by the variation of the this anomaly theory, which is also given in terms of this background for the symmetry G. And here in both actions, the B is a classical field. But when we think about symmetry inflow, here we have the symmetry TFT action, and it's given in terms of this field beta, and beta is a dynamical field. So, and also just like anomaly inflow, we have a D+2 dimensional action, which is I call S inflow. And this one is given in terms of this field B, which is also a dynamical field, different from beta. And the way B and beta are related is that beta are the gauge degrees of freedom of B. So, so again, the relationship we have that the gauge, if we do gauge transformation of this action and impose some boundary conditions, we get D of the symmetry TFT action in terms of these gauge degrees of freedom beta. Okay, so let's look at the example of Maxwell in more details. So here we know we have a P-form connection AP. So we are in D dimensions and we have this is our field, gauge field AP, and it has field strength FP plus 1. We can write the Maxwell action as minus 1 over 2 squared F just star F. Now, like I said, we want to describe a theory, write a theory where it includes the dual description. So we could write this action in terms of the dual field, but what we prefer to do is to have a theory that includes both this A and A dual. So we can think about Maxwell as edge mode of this generalized Maxwell BF theory. And this theory has these gauge fields B and C. And these are dynamical. We have these actions for B and C, and also we have a BF term, B with DC. So looking more closely to this action, we see that if we take so these away from the boundary, this theory is a massive deformation of the BF theory. So these C and B have masses, but if we take the large coupling limits of E squared and E prime squared going to 0, we get just the BF theory. And we see that specifically C and B are flat fields in this low energy limit. So if we parameterize a local neighborhood of the boundary of Y by some manifold X, which is the boundary manifold times some interval, where tau, we define tau to be the coordinate on this interval, then we can take some asymptotic solutions for this B and C that localize on the boundary. So we see that near the boundary region, these become the Maxwell fields on the boundary. And from the equations of motions of this action, we can see that we must have df, which is d of a, and dg, which is d of a d minus p minus 2, must be 0. And also we find that s star of f is g, and these together give us the Maxwell equation df equal d star of f equal to 0. Now, we also want to split this region into, yes.
Yeah, these are not equality between F and star F and
S star of F is
yeah. How does it appear?
So F and G are dual to one another. Sorry, I'm not sure I understand. So how does it?
Yeah, but when solving that one higher dimensional BF theory, so by solving a kind of equation motion, does it automatically appear? Or
Yeah, so by equations of motion of fields of B and C, and then substituting these answers into those equations, those give us these equations.
So that duality is just naturally appear, and alpha and beta equal beta.
Yeah, this one also is imposed too. So this is also imposed because we need these fields to be flat by the boundary conditions. Yeah. Okay, so we also like to think about the near boundary conditions. Sorry, to the region, think about the region near the boundary. So here now I'm taking some T alpha where for T much less than T alpha, for T less than T alpha, we have that this e to the alpha tau is much less than 1 in this region. And by a gauge transformation, I can also write B and C. So remember we had B and C being of this form, we have e to the beta tau times A, e to the alpha tau times A. And now by gauge transformation, I can write them as some other form as 1 minus e to the alpha tau f and 1 minus e to the beta tau g. And in this, away from the boundary, we see that this is much less than 1. So these B and phi become f and g. And so away from the boundary, they don't vanish anymore, but they become pure gauge. So we have that f is dA and g is dA dual. So B and C become pure gauge fields away from the boundary. And so we see that the Maxwell fields are exactly gauge parameters for these the ball fields B and C. Or alternatively, we could take the boundary condition where we don't have B and C vanishing, but the class of B and C vanishing. So they are pure gauge at the boundary. And in this construction, we can just take the action to be the BF action minus some boundary term. And we will reproduce the same results. So in particular, we have that in the large coupling limits, we just get the BF theory. And in this limit is what we are interested in when we want to do the dimensional reduction and study the symmetry TFTs. So we want to focus on this term. Now, again, to get the symmetry TFT from dimensional reduction, we want to make sure we want to reduce this this action on spaces with non-trivial topology, and so analysis in terms of differential forms is not gonna be good enough for us. So what we want to do is to define our gauge fields in a way that they contain information about the non-trivial topology of our space. To be more specific, let's think about some gauge field A, which has field strengths F equal to dA, and we know this equality is only true locally, so we have to define a manifold with different patches, and in each patch we have F equal to dA locally. But globally, it is not well defined. So how do we fix that? Let's think about the holonomy function. We can write it as the e to the 2 pi I of integral of the gauge field over some loop. And then if we take m to be the bulk, so if we take w to be the boundary, sorry, m to be the boundary of some manifold w, then we can also write the holonomy in terms of e to the 2 pi I integral of the f. And equating these, we see that we must have integral of f minus delta a over w is an integer, since this is 2 pi I times n number. So we find that there should be some integer n, some integral cochain, which is integer valued, that relates a and f in this way. And this is a globally well-defined equation. So we can write the gauge field as the dot of a gauge field by these triplets n, a, f, where they are related in this non-trivial way. And more formally, this A is a representative of a differential cohomology element. And this is originally studied by Chigger and Simons, and also in a different formulation by Hopkins and Singh. So N in this setup is called the characteristic class of A, and it encodes the topologically non-trivial information about the gauge field. Now, so that we have this kind of formulation of the gauge field in terms of topology non-trivial fields, we can again think about how to write the BF action more carefully in terms of these fields. So we have two fields in the BF theory, A and B, and I write the action as A times B, A hat times B hat, I mean. And if we restrict to fields which are topologically trivial, so they have n equal to 0, we just recover the BF action we know, which is A times FB or F times DB. But we can also have the case when this F is, this gauge field is flat, so F is 0. And in this case, if you were just doing differential form analysis, you would get this BF theory is 0. But that's not the case in topologically non-trivial settings, and we still have a non-trivial action in terms of A and N. Or we can write N using this formula as delta A, and we would have integral of A times delta B. Okay. Now, going back to Maxwell theory, now that we have defined these BF action in terms of these topological non-trivial fields, we can, well, more specifically write B and C in terms of these characteristic classes of B and C. And then now we impose the boundary condition that the classes of these gauge fields is 0. This means that they are just pure gauge and they can be written in this form. So N is some delta of F, and then B is like we have before, 1 minus eta alpha tau FB, where FB is FB plus delta lambda B. And here, it's important to note that we have this F, so we have this integer cochain, which tells us about non-trivial topology, and then we have also a real cochain lambda. and then the field strength is given by minus d to the alpha tau fp. So if we go to the near boundary region and ignore the exponentially decaying terms, the exponential terms, I mean these parts, then the gauge fields, they will be, these B and C would be given just in terms of f, little f and lambda in this way, in terms of some integer cochain and some real cochain. Yes.
Can you clarify what is this bracket and why can they because B and C are dual conjugated fields. So in general, I don't expect that they can simultaneously be assigned to their Dirichlet combination.
So B and C are just the two gauge fields in.
Yeah, but they are conjugated.
Why do you say that?
Because it's a DLC, like BBC, and then you have you can cannot very contact from the
They are not like electromagnetic dual in this in that sense. Yes.
Maybe I misunderstand it's a bracket.
So this is what we had before here also.
Yeah, it's not just B wedge DC.
Yeah, so if you write this out, we'll have different parts, which includes this part and this part. Okay. Maybe we can discuss more after. So how do we actually, now that we have written the action in terms of these B and C, we want to dimension reduce it to get the symmetry TFT. So we can. So now, if you notice, I have written the equation again, but in terms of Lagrangian rather than the actions. And this is important because we should be careful, because here Y is the symmetry TFT of a tower in one-dimensional lower, and we are extending Y to Z, and we have boundaries of boundaries, and that may seem troublesome. But if we look at Lagrangians and work locally while maintaining information about the topology of the space by having these non-trivial fields which encode topologically non-trivial information, we can work locally and just do the integral of the Lagrangian and not run into a problem. So in this equation, we have that the gauge transformation of this BF action gives us D of sim TFT. So let's look at the gauge transformations. In this case, B goes to B plus D beta, and C goes to C plus D gamma. So when we do the gauge transformations and impose the boundary condition, we have that the BF action is just dB times D gamma. Let's take L to be a three-manifold, which is the Lenza space, so it has interesting topology. And then we can reduce these fields on this L times Z. So beta can be written as X times T, where T is a cycle in S3 mod Zn, and X and Y, these are fields which are only live on Z. Then we can do when we do the integration, we can just integrate over these t's, which are cycles in here, and we end up with n times delta x cup delta y. This should be really 1 over n, depends whether we take x and y to be z valued or z or u1 valued. So then we find that delta of the sim-TFT action is given by this integral of 2 pi n x cup delta y, which is the so if we start from the Maxwell theory, this would be y would be one-dimensional, reducing on S3 mod Zn, and this is a non-trivial one-dimensional theory that we obtain in this way. Now, we would like to generalize to the case of a string theory. And again, we want to write a bulk action for supergravity and drive the sim-TFT via dimensional reduction. Now, this is interesting because there are just so many examples. I've given just a few here, and there has been so much work in trying to understand the symmetries of these theories and the symmetry TFTs. So there's some earlier works studying the BF theory part, well, from a non-Lagrangian perspective, to so many more works trying to understand the sim-TFT from dimensional reduction. Here, in this paper, we studied this sim-TFT by dimensional reduction of a string theory, but there we did not consider a bulk action for a string theory. So what we looked at was the topological Chern-Simon action in a string theory, and we reduced that. We found the sim-TFT action. But that's we realized that is not good enough, because the BF theory, particularly, it comes from the self-duality of fields in a string theory, or comes from electromagnetic duality. So to get that, we need to do this bulk construction, and so that's what I want to discuss now. Also, we should note that to construct this bulk action for symmetry TFT, we need to make sure that this bulk action is consistent with anomaly cancellations in string theory, and I'll also mention that. Okay, so in general, just a little bit more on anomalies. So, for example, if you're interested in type 1 string theory, we know that the anomalies of fermions. So let's just look at the 8D supergravity theory, maybe a bit simpler. And here we have fermions which are gaugino in the adjoint of the gauge group and gravitino. Here they have some anomalies, and it's required that they cancel via a version of Green-Schwarz mechanism with anomaly with a Chern-Simon theory for a two-form field B. Now, in a more modern language, we have a dynamical field B in d dimensions. We can define these currents JE as a star of dB, and electric current and magnetic current as dB. Then we see that we have a two-form U1 symmetry associated to the 3-form current, and a d-4 form U1 symmetry associated to the dual currents. And this Green-Schwarz mechanism can be understood as the anomalies of these higher form symmetries canceling the anomalies of the fermions. And this was discussed in these papers, and this 8D supergravity specifically in this paper. So let's say that Q is a D plus one-dimensional theory describing the anomalies of these higher form symmetries. And then Q has an action in terms of these 3 forms C and D-3 forms B, which realize this 2-form field B and its dual as the edge modes. And in addition, we want to cancel these anomalies of fermions really by turning on background fields for these higher form symmetries. And so what's the action for these in D plus one dimension? Well, it's nothing but what we talked about before, except that now we have turned on this background field for the 2-form symmetry. And we have added the anomalies of these higher form symmetries here. Now, if you take again the limits where E and E prime go to infinity, and we carry out the path integral over B, we find that B becomes a Lagrangian multiplier, and we set C to be AE, and the anomaly is just given by 2 pi I Q of A. And this is the anomaly that would be canceling the anomaly of the fermions. So now the equations of motion before for these fields B and C was that d of a star of FB, where FB is d of B, is equal to 2 pi alpha FC, where FC is d of C. But now turning on the background field, this is modified to FC minus FA. And so we can define a field H, which is a star of B at the boundary tau equal to 0. And then from here, we see that d of H is minus FA at the boundary. And so we can write H as dB minus the background field AE. And this is familiar from string theory. So then to cancel the anomaly of the fermions, we specifically need this FA, the gauge field for this AE, to have this form. So it's given by some instantaneous density. Now we want to generalize to type 1 and type 2 supergravity. Here, again, we want to define a bulk action for some dynamical field B in 11 dimensions. And instead of a BF theory, now we have a Chern-Simon because of the self-duality of the string theory field. So we just have one field rather than two. And then, as I said, these string theory fields are given as gauge degrees of freedom of this dynamical field B in 11 dimensions. So these are in 10 dimensions. And then here, to work in a precise language, we want these B's to be valued in real or complex differential K theory. So for type 1, we have real K theory, and for type 2, we have complex K theory. And then reducing this action, this bulk action, again, just like in the case of Maxwell, will give us the SymTFT. Okay, so again, just like in the AD supergravity case we just discussed, we write the anomalies of the RR fields as in terms of some anomaly theory, Q of B, and then the anomaly of fermions we know is given by the eta invariance in the D+1 dimensions in 11D. And then the total action would be Q of B plus eta of B. Again, to make sure anomaly cancellation, we want to take the background field, turn on the background field A, which now is valued in K theory, and then just like we had before, we find that for anomaly cancellation, we want Q of A to be eta of A. So just to give you an idea how these actions look like, I won't go into too much details. Let me tell you how to write down these actions in terms of the gauge fields. And now here, well, first we like before, we want to write down the actions in terms of some bulk fields B and C, and then so we had in the previous slides, we want to write it in terms of some, just here in terms of B, but then like we had in this slide, we want to integrate over this B, where here now we just have one of these terms and we have B wedge dB. And then we want to, integrating over B will give us that the action is just given, the action we are really interested in is given in terms of the background field Q of A. So skipping those steps, we can just write down the the action in terms of some quadratic refinement. So this action was actually given in this paper. So here A is an element of K0, so it is it's in complex K theory, and this A, so it's associated with so well the dynamical field B we write is associated to the realizing the string theory fields as background fields. So in type 2B we have that the fields are valued in K-1 of M. So when we go to one dimension higher, these there's a shift by degree, and we get K0. And then this action can be written in terms of, so here A, let me be more specific, V here is a bundle in K theory, B is a connection on it, and C are forms of odd degrees. And then we have this C wedge D star C term, and then we also have R here is the Riemann curvature associated to M, and then we have these other terms. In fact, if you take factorize, like complete the square here, we can write C as C plus Cherenkov of B. Well, if we go into one dimension higher, we can write DC plus Cherenkov of B times C star times D of C star plus Cherenkov of B star, and those quantities are similar to H, which are gauge invariant quantities. And then, so this is the anomaly associated to these RR fields. And then we also have anomalies which are associated to the fermions. In type 2B gravity, we have the gaugino, dilatino, and gravitino. And these can be written in terms of the eta invariants. So we can also write down the anomaly polynomial using the APS index theorem. And we expect the anomaly to cancel here. So we don't actually need to cancel these against each other, I think, because we are in type 2B and we don't have Green-Schwarz anomaly cancellation. Here, this is the anomaly corresponding to gravitino in terms of this gauge field B, which is a connection of the bundle. And this Ty is the tangent bundle. So these are just given in terms of R. Okay, so, and then going to type 1 string theory, similarly, we have some anomalies associated to fermions. We have gaugino in the adjoint. So now data invariance is slightly different from here. And we can write the total anomaly in this way. And again, using the APS index theorem, we can write down the action in terms of some 12-dimensional anomaly polynomial, this action, which is given by x4 times y8. And that's in the usual sense of Green-Schwarz, anomaly needs to cancel through anomaly inflow with a 10-dimensional Chern-Simon action. But in this more modern perspective, we have constructed this action. We can construct this action which is related to x4 and y8, which cancels the anomalies associated to these fermions. Now, this is as far as we got. We are trying to work this out, and the idea is that to use this action to study symmetry TFT. So now we are starting with this supergravity action in 11 dimensions. We put it on some manifold y times L, and then, well, one way is to just write down the 10D topological action in a string theory and go directly down to y. But in this construction, we saw that we can construct some action in 11 dimension, and then we can integrate over L to find some action on Z, or more specifically, we look at the Lagrangians, we find the we look at the gauge transformations of this action on Z times L. And then when we integrate over L, we'll find D of sim TFT. So using a Stokes theorem, we can just go to the boundary and write down the boundary action. So yeah, this is what we'd like to do next. Okay, so this is all I have to say. Thank you for this.
Thank you very much. So, question, discussion?
Sorry, I think you explained it, but on the previous slide, when you gave the eta invariant,
Mhm.
what's the third contribution, the last contribution to the eta invariance? Where does
This
that?
one.
Right.
So this usually we write this as so we can write this as D of Dirac times the adjoint bundle. So this is related to the Gaugino transforming in the adjoints. So usually we can write this as so we write this as
Isn't
A hat times the Pontryagin character. Well, if you use the index term, we can write it as the A hat times the Pontryagin character of the B field, and then that's given in terms of the adjoint.
I see. So this B, so this thing you were calling A hat, I was thinking of it as an RR field, but is that not true?
Sorry, A hat, which one?
So B is supposed to be the connection component of some differential cohomology element A hat.
Yes,
Right.
sorry, yes.
Okay,
that's it.
and how do I interpret that A hat then?
So here, instead of K0, we have real K theory. So we are thinking about KO theory. And so V would be a real bundle and B would be a connection on it. So we can write can I write here? So we can write this V as the symmetric part plus the anti-symmetric. So how do you write the anti-symmetric? The symmetric by symmetric. I don't know. Of V. And we are interested in the adjoint parts, which would be correspond to the antis.
Thank you.
Other questions? No? Okay, let's thank to Saga again.
Thank you very much.
Thank you very much for the nice talk.